All right, let's jump right in. Today we're going to get into the real nuts and bolts of how a quantum computer actually works. We're talking about the fundamental actions, the verbs of the quantum world, known as quantum operations. This is literally how information gets manipulated in this incredible new form of computing.
Okay, so let's start with a simple analogy to get our heads around this. Think about the computer or phone you're using right now. It runs on classical operations, which are basically like light switches. They're either on or off, a 1 or a 0. Super clear, right? But quantum operations, they're more like a super sophisticated dimmer dial. They can be on, off, or an almost infinite mix of possibilities in between, and all at the same time. And that is where things get really interesting.
So to really understand how this quantum dimmer dial works, we've got to learn the grammar of this whole new computing language. And it all starts with one single master rule. And that master rule is called a unitary transformation. Just think of it as the ultimate law of the land in quantum computing. It makes two huge promises. First, every single operation is reversible. You can always rewind the tape, which means no information ever truly gets lost. And second, all the probabilities have to add up to 100%, always. The universe, it keeps a perfectly balanced checkbook.
So this idea of reversibility it's absolutely crucial. It's a total break from the classical world. I mean, think about it. When you delete a file on your laptop, that information is gone. Poof! But in the quantum world, nah, that's not how it works. Being able to go backwards is key.
Okay, so we've got that master rule in mind. Now, let's get into the fun stuff, the actual moves a qubit can make. We'll start with the solo acts. These are the operations that only affect a single qubit at a time.
These single-qubit operations are the absolute foundation of any quantum algorithm. You can picture the qubit as a tiny sphere. These operations are like giving it a super precise spin, or a little nudge, to rotate it to a new position on that sphere. Every little rotation carefully changes its quantum state, tweaking the probability of it being a 0 or a 1 when we finally decide to look at it.
For example, you've got the Pauli gates, which can act kind of like a classical NOT gate, flipping a qubit's state from a 0 to a 1. But the most famous one, the real star of the show, is the Hadamard gate. This thing is the magic wand. It's what puts a qubit into that bizarre state of superposition, that mind-bending state of being both 0 and 1 at the exact same time.
But look, as powerful as it is to spin one qubit around, that's not enough to build a computer that can change the world. The real power, the secret sauce, really comes out when qubits start interacting with each other, when they start working as a team.
And this teamwork is possible thanks to a phenomenon that Einstein famously called spooky action at a distance, entanglement. It creates this unbreakable link between qubits. So operations like the C-NOT, or the controlled NOT gate, can take advantage of this. It'll flip the state of one qubit only if its entangled partner, the control qubit, is in a specific state. This is how we start to build complex logic, where one qubit's action depends entirely on another's.
Okay, so we've done all these amazing reversible operations. Our qubits are in superposition, they're all entangled. But how do we get a useful answer out of all this? Something we can actually read.
Well, we do it with a special kind of operation called measurement. This is the moment of truth. It's when we peek into the quantum world. The instant we measure, that whole cloud of possibilities just collapses, forcing the qubit to pick a side. It lands on one single, definite classical value, either a 0 or a 1. The quantum mystery suddenly becomes a classical fact.
And this shows a really important difference. Unlike all those unitary operations we talked about, measurement is a one-way street. Once you measure and that state collapses, you can't undo it. You can't put the genie back in the bottle. The quantum weirdness is gone, and you're just left with a good old classical bit of information.
Now, everything we've talked about so far has been in a perfect, ideal world. But in reality, quantum systems are incredibly fragile. I mean, the slightest little vibration, a stray magnetic field, a tiny change in temperature, what physicists just call noise. It can act like a bully, knocking our qubits out of their delicate states and totally wrecking our calculation.
So to deal with this, scientists use this really clever concept called a quantum channel. And no, it's not a physical pipe or wire. It's a mathematical model. It's a way to describe exactly how that noisy environment is attacking and messing up a quantum state. Because if you can model the attack, you can start to build a defense. And understanding those errors is the first step toward fighting back. The defense is called quantum error correction, and it's basically like building a protective shield. It uses helper qubits to keep an eye on the main data qubits. These helpers can tell if an error has happened and then trigger other operations to fix it. all without ever directly looking at and collapsing the precious quantum information we're trying to protect. It's pretty genius. So we've got all these building blocks, right? Unitary gates, entanglement, measurement, error correction. So why go through all this trouble? Why does mastering them matter so much? Well, the answer is what we can build with them.
This is where it all comes together. By stringing these basic operations together in just the right order, a Hadamard here, a CNOT there, followed by maybe hundreds more, we create a quantum algorithm. And you can think of each algorithm as a unique key, carefully crafted from the sequence of operations designed to unlock a problem that was impossible to solve before. And this table gives you a little taste of just how powerful these keys can be. An algorithm like Shor's, built from these exact operations, could theoretically smash the encryption that protects almost everything we do online. And Grover's algorithm could search a huge, totally random database in a heartbeat. We're not just talking about being a little bit faster here, we're talking about solving problems that are flat out impossible for even the world's biggest supercomputers today. So when you boil it all down, that's what these quantum operations are. They're the alphabet of a completely new language for talking to reality. The gates, the measurements, the error correction, these are the letters and the grammar. And right now, we're just learning how to spell our first words.
Which, of course, leaves us with the most exciting question of all. As we get better, as we go from writing simple sentences to composing epic poems in this new quantum language, what incredible problems, in medicine, in material science, in understanding our universe, what are we finally going to be able to solve?